Hello, my name is Alan Zhang, and this is Lab 2 for motion of a falling object in the course Physics 2211 with Professor Curtis. So, the purpose of this lab is to observe the differences of 3 different models through comparison. These models include 2 computational models, one with drag, one without drag, and then finally, our last model is our actual model, which is our experimental data, which is this one. So, the data recorded from the experimental data was through the software called Tracker, an image of the software shown below, and there's also a video of how it ran. So after this, we had to utilize something called a glow script, which is to simulate the 2 computational models. So this model in particular is the one with drag. Here's the code. And there's the data. So after the drag model, we created one with no drag. Here's the code. And here's the data. So looking at these 2 codes, the only difference is the b-value. So what the b-value is just the constant of drag. So this constant was found through plugin checks until the end value of the model with drag was similar to that of the experimental data's last position. So to understand the computational models a bit more, we have to look into the fundamental ideas of physics. So this lab in particular used Newton's second law, or F is equal to ma. So the steps shown in this image is using this Newton's second law to eventually lead to position change, which is essentially what the program is doing to find out where the ball will be after a certain amount of time, which is, in this case, 0.45 seconds. So as you can see here, we start from Fnet is equal to ma, break a and sound into velocity average over time, and then from here we found out final velocity, and then with final velocity we were able to find the final displacement. So now we can go back to the data. The initial condition of the ball is that it must be at rest, and to prove this in the simulations, in both computational simulations, we have the ball velocity vector as all zeros, which means it is at rest. And then for the experimental data, the ball is being held up, which means it is also at rest. So in this case, or in all these cases of the experiment, the ball is our system and the air is the surrounding. For the experiment, the ball is dropped and recorded and then placed into Tracker as stated before. Tracker is then used to track the position of the ball and how long it takes to hit the floor. From this, we're able to get actual data. So after the experimental data, we had to get the computational data, which we used the codes to create 2 simulations, the glow script codes. So one simulation with drag or air resistance, which is caused by the interaction of our system, the ball, and the surroundings, the air. So because of drag and air resistance, we have to count the drag coefficient as stated earlier and replace it into a variable that will then be used to calculate our acceleration, then to velocity, and eventually position. So that's the model with drag. So our second model is essentially the same code, but this time we just completely removed the drag coefficient because the simulation was an ideal situation with no drag. So using this data, an Excel sheet was created, and then a graph was created as shown here. So from this graph, we can see that the no drag model fell the fastest, and we can see that because it reached the ground faster, in theory, according to the graph. So in this case, we have to look very, very closely, but you can see the hints of the no drag model below the drag model right here, where we can see a little black behind the orange. The black is the no drag model. So the reason why these values are so close together in this case is because our drag constant was so low. However, in addition, we see that the simulation with drag, the orange, fell faster than our actual data. And we can see that because the green, our actual data, is above the simulation data. And then this is really likely due to a source of error, because the actual data should look even closer similar to that of the simulation data with drag. And this is likely just the source of error with human error, like not clicking the ball center of the ball in Tracker and recording situations since the ball is recorded at an angle. So that was that record from my lab, and now we have to move on to what if and what does it mean. So would any of my models correctly predict terminal velocity? So first, terminal velocity is essentially where drag force equals that of force of gravity, so the net force of an object is 0. So I answered this question with a no for many reasons. The first of which is the time it was recorded. It is simply too short, and then the drag constant or coefficient is not accurate because it was done through a plug and check method instead of an actual mathematical method. So what if an object was thrown from rest instead of dropped from rest? My answer would be that terminal velocity would be the same because after it is thrown, the only forces acting on it would be gravity and drag. So after a period of time, the Fnet would be 0 again, and velocity would even out to be what it would have been if the object was simply dropped from rest. Thank you.